Assalamualaikum. In this session, we are going to learn about problems and how to solve the problems. The problems are regarding the data of organic spectroscopy such as UV-VIS, FTIR, mass spectrometry and NMR. All this data of spectroscopy is used to elucidate the structure of organic compound. In order to confirm the structure of organic compound, we can use the formula of double bond equivalent to identify the presence of how many of double bond and the presence of ring inside the structure. The formula of double bond equivalent is CXHY. Based on molecular formula given, X is equal to number of C, Y is equal to number of hydrogen. Based on this formula, we know how much double bond and how much ring presents in our structure. Let's see the example of this molecular formula. C6H6. We insert the numbers of this example inside our formula. When we calculate, it becomes 6 plus 1 minus 6 divided by 2. Total double bond equivalent is 4. The structure predicted like this. Is it confirmed to be 4 double bond equivalent? Let's count how many double bond and ring inside this structure. This is 1 double bond. This is 1, 1, 1, 2, 3, and the ring is considered as 1. Total numbers of double bond equivalent is correct, there is 4. That's how the double bond equivalent used to confirm our structure. Let's see the next example, which the presence of heteroatom like oxygen, C3H8O3. In this case, for the formula of double bond equivalent, the presence of oxygen will be ignored. In this case, C plus 1, so the number of C is 3, the number of hydrogen is 8, total number of this structure is 0. Means the structure, there are no double bond and there are no ring. The structure is a straight chain. Next example, where's the presence of heteroatom, which is halogen, inside our structure. If the molecular given like this, C10H7 with the bromine, what we will do with the DBE? How to calculate? Based on the formula C plus 1 minus H divided by 2, so we know the number of C is 10 plus 1, 7 is the number of hydrogen. We see what is the number of 1 here. The 1 here is the number of how many halogen presents in our molecule. In this case, there are 1 bromine. That's why they added with 1. If halogen presents in the molecule, we have to add it in the DBE formula. 7 plus 1 is divided by 2, so total DBE become 7. Next example, if nitrogen presents in our sample. If nitrogen is present in our sample, the formula of DBE must deduct the nitrogen atom. We see the example when the molecular formula given the numbers of nitrogen. C12H12 nitrogen 2. Based on DBE, how we can calculate the DBE? 12 is the number of carbon plus 1 divided by 12 is the number of hydrogen, and this 12 need to divide by 2 because the presence of nitrogen, and divide by 2. Total number of the DBE is 8 for this structure. Let's see the example are more complicated like this. Oxygen, what will happen? We will ignore the oxygen. Nitrogen will be added. Based on DBE, the total of the answer is 4. As I can conclude based on DBE formula. What is the purpose of DBE? You want to determine how much of double bond and ring presents in the structure. This DBE can confirm the structure whether it is correct or not. The formula of DBE is C plus 1 minus H over 2. If the presence of halogen, we need to add the halogen. We need to add here H plus halogen. How much halogen? And if oxygen presents in our molecular formula, we have to ignore the presence of oxygen. And if nitrogen present, we have to subtract the nitrogen here. So I can simplify the formula of DBE with the presence of heteroatom with the formula of ice. Add halogen, ignore oxygen, subtract the nitrogen. Next part, we see the problems in detail. If given the spectroscopy data like this is the mass, the MS data, this is the FTIR data, and this is a carbon-13, and this is a proton NMR. And the question asks you based on this raw spectroscopy data, the question asks how to elucidate the structure based on this spectroscopic data. We see the problem 1 is to identify the examine the structure of compound based on mass spectroscopy, IR spectroscopy, C13 NMR, and 1H NMR spectroscopy. Let's see how to solve this problem. If we can see, the molecular formula of this molecule is 72, and the loss of here, the first fragmentation pattern will be 57. 52 minus 57 is loss of CH3, and the next loss is 72 minus by the 44, it becomes loss of ethyl group. Only this information we can get. In details, we need to go for the next part, which is FTIR, NMR for both proton and carbon. In FTIR, what is telling us? This is around 2,900 to 3,000 frequency, and this wave number shows us the presence of CHSP3, and the more important functional group here is the presence of carbonyl group, which is 16,000 something or 17,000 something. All the pieces of information from different spectroscopic data will be combined, and lastly it will be elucidate the structure. See the carbon-13 NMR, how many peaks presents? 1, 2, 3, 4. These 4 peaks shows us that the presence of 4 carbon. Next, we go for proton NMR. If you can see 1, 2, 3 peaks with the integration of 3, 3, 2. What integration means is telling us how many hydrogen presents in the atom. We have to, based on this raw data, we have to make this table, this 4 column. The first column is chemical shift, the second column will be the multiplicity, and the third column integration, and the last one is the assignment. We have to make this table to make us easy to interpret the proton NMR. In this case, the chemical shift for the first signal is 1.1. We see the multiplicity is triplet, is the 3H is the integration. Based on this, we write down first all the information in this table. After that, we do the last part will be the assignment. And the next signal is 2.2. This is the singlet peak. Multiplicity is singlet and integration is 3H. Next is 2.4. The multiplicity is quartet and 2H. If we can see, the integration is 3H, 3H, 2H. In NMR, proton NMR, we should know that this is the trend or the significant CH presence in the organic molecule. Methyl, CH3, methylene, CH2, methane, CH. Others, if fall in the more further downfield, is considered as unsaturated. In this saturated region, we have to know if we assign 3H, it means what? It means the presence of CH3 because this H is 3. That's why integration is 3. If you see the integration is 2H, means the methylene proton presence. That means there's a CH2 present. If the integration is 1, it might probably methane with a CH. If the integration is 4, it means what? 4H. 4H, you know that there might be 2 group of CH2 or 4 group of CH. Only 2 possibility. If the integration is 6H, the most possibility is 2 group of CH3. That's how we can recognize the presence of signal for the proton in 1H NMR. Based on this knowledge, we can do the assignment in this table. Before we go to the assignment, we have to recognize the chemical shift for this typical signal. Mostly, methyl group will fall in 0.8 to 1 ppm. If more than that, means this methyl group have attached to the electronegative atom. Same goes to the methylene. Without referring to the table behind as appendix in any your assessment, you can easily recognize the presence of these three signal. CH2 always presents in 1.2 to 1.8 ppm. Methane group, we always present 2.0 to 2.5 ppm. These three signal always remember because they will be used in the problem solving part. And C double bond C is more downfield. If you can see 4 to 6, aromatic is 6 to 8. Without referring the table in appendix, you can know the position, which one is CH3, which one is CH2, which one is aromatic, which one is C double bond C. Next, the last part will be the assignment. As I mentioned just now, 3H it presents, it means CH3 presence is our molecule. C, how it coupled with, how we can identify the couple with, mean triplet. Triplet, if the rules of n plus 2 means what plus 2 become triplet? 2 means this CH3 is coupled with CH2 because 2 plus 1 become triplet. That's why the answer is CH3 coupled with CH2. And next information, CH3 isolated means there are no couple, there are no neighboring proton. And CH2 coupled with CH3. How we can know CH3? Because the signal is quartet, n plus 1 is equal to 3 plus 1 equal to 4. So 4 is quartet multiplicity. Means CH2 have a neighbor of 3H. That's how we complete the assignment in this column. So, based on the structure, we will combine the data from the proton and carbon 13 to become a complete structure. As we can see, the signal of 1.5 from previous slide, we can see 1.1 is CH3 coupled with CH2, means CH3 besides CH3 is CH2. See, besides CH3 is CH2, correct? Follow the table. And this CH3, if we can see the table, this CH3 is isolated, means there are no neighboring. Is it correct in our structure? Let's see the confirmed structure. CH3, there are no neighboring proton. This is correct. CH2, let's check the CH2. How many multiplicity will be the quartet? Check the table whether this is correct or not. Okay, CH2 now is coupled with CH3, means these two are related each other. This CH3 beside CH2, this CH2 beside CH3. So this is the same part of the structure. This is a different part. Because this is a singlet CH3, I say the normal region for chemical shift for CH3 is 0.8 to 1 ppm. In this case, is it fall in that region? No. This is more quite de-shielded, means downfield, means it attached to the electronegative atom. We see the structure whether it is correct or not. Yes, this CH3 is direct attached to C double bond O. Based on all NMR data and the presence of C double bond O through the FTIR, we confirm the structure is correct. Based on carbon 13, we determine the chemical shift based on the value, which is 0 to 15 normally CH3. The value for 15 to 20 is equal to CH2, and 20 to 30 is for the CH. In this case, 32 is more quite downfield because it direct attached to the C double bond O. After confirm all the data through proton NMR, carbon 13 NMR, FTIR, we recheck again whether it fits or match with the MS data. So this 15 is this part, and this is 12. So C here have C 12, and 16 is oxygen, and this CH2 is 14, and this CH3 is 15. So the total molecular weight is 72. So confirm the structure is correct. That's how we solve the problem. You have to go one by one, a piece of information from spectroscopic data and reconfirm for the last stage. That's one example. Next example will be, in this example, it's just given you in the form of text. They are not given you the information through the spectrum. Let's see the example 2. An organic compound with molecular mass 69 is transparent above 200 nanometer. The absorption band in infrared are 2941, 2273, and 1460. In one HNMR, two signals are found. One septet 2.72 with a 1H integration, and coupling constant is 6.7H, and another doublet at 1.33 6H, and coupling constant is 6.7 Hz. In C13 NMR, four signals are found at 19.8, 19.6, 19.9, and 119.4. Explain and predict the molecular structure of the compound. We can either choose to answer in form of text or table like previous example. I show you how to solve the problems with the text answering. This is based on the data of the FTIR. This is the data of, let's mesh some data from the mass first. Okay, if you count the amount of the structure suggests the presence of, in this case, they are directly go for the interpretation of the proton NMR first. A subset and a doublet, only two signals in the NMR, proton NMR. Coupling constant, why coupling constant? Suggests us that in this case there are presence of unsaturated. CH3 septet with the how many integration? 6H. 6H means CH2 is one part becomes CH3, have two group with the attached with the CH. How we can use this? How we can solve this problem without doing the table is quite challenging, so that's why I'm telling you the easier way how to solve this problem is based on the developing the table. How they know this one? Stage 2, this one is expert, can know that a substat and a doublet means a substat is 6 signal, cause this one a substat, 6 plus 1 become 7. So means they have 2 group of CH3, that's why they contribute the subset. And a doublet mean there are 1 neighboring proton, so they cause the doublet. And plus 1 is 1 plus 1 is 1 plus 1 is become 2. That's why it's doublet. This is only expertise can imagine the answer like this. If you cannot imagine like this, don't answer like this way in text form. Better go for the table form. I'm not going to go detail in this text form because it's quite challenging, because you are not really understand how it can be presence of this. This one is come from a book answer. I'm suggested you to draw the table. Okay, in this case they have 3 signal of FTIR, so we know each signal we have to interpret 2941, 2273, 1460. In this case 2941 is for stage sp3, 2273 we predict the presence of C triple bond N, and 1460 is the presence of CC. Correction, this is CC. Sorry, 1460 for CC. It's not CH. This one is CC. Next is proton NMR signal. They have 2.7 to 1.33. I just say that 1.33 always for the CH3 region. So we know that this is the fixed region. How why become 6H? Means they have 2 group of CH3 and 2.72. This is always the region for what I say just now, the region for the 3 signal, methane, methylene and methine, methyl, methylene and methine, the fixed region. You have to memorize that one. Based on this region, this is the region for CH. We know the integration also 1H, so this confirm that only CH is present. And this is the signal of 4 carbon signal. So they have a 4 carbon. This region is for CH3 region, and this is near to the electronegative atom. That's why it fall in more downfield. Based on all the data of spectroscopy, we can elucidate the structure. And 1.33 is for CH3 for both group. Integration is 6H. We can check back, and this signal will be doublet in multiplicity, and this one we can septet because this 3 plus 3 6, so this signal is 2.72, and the full of interpretation will be this. Recheck with your table and reconfirm with the mass, and total mass is 69, so the structure is confirmed to be this one. That's all for 2 examples. We will continue with the next example later. Thank you.